Hello everyone. I hope you are doing okay. Today we'll be talking about when the data is not linearly separable, how do SVMs handle that, and we'll also talk about the famous kernel trick. Okay, but before that, let's just recap what we have learned about linear SVMs. So imagine imagine you have 2 points. Okay, here as you see here, like, and the data is evidently linearly separable. So a linear SVM finds the best straight line that separates these 2 points with the widest possible margin. So that is what we do here. Maximize the margin. So this line acts as a decision boundary, and the points closest to these lines are called the support vectors. So in this case, this would be support vector, and probably this would be the support vector. Okay, but here's the catch. What if the data is not linearly separable? Let's say we have a data inside an annular ring, and the two classes are separated by the same annular ring. What do we do? So there is no way you can probably draw a line and then separate groups. So this is a perfect example for nonlinear data. So the answer lies in but the general idea here is that the input space can be mapped into some higher dimensional feature space where training set, the data points, is separable. So we have X here. We need, let's say we have a mapping function called 5x, and trivially we are just gonna okay, so what the 5 will do is it will say map the training set into a higher dimensional feature space. Okay, so we'll have a uniform plane in the middle which separates the two classes. And the good thing about this is that the space where the concept of the dot product is well defined is usually called the RKHS, or reproducible kernel Hilbert space. And as I was saying, right? So the good thing about this is we simply need to know the dot product. So I had to pause the recording for some work that I had. Anyway, continuing. So where was I? When the data is non-linearly separable like this here, we use a mapping function to map it to a higher dimensional space where you can have a uniform plane which separates the two classes, right? So now most of the times you can introduce a three-dimensional play extension, I mean along the along the third dimensional, and usually you will find the data is separable. What about what if we were to jump to a 6-dimensional plane, 10-dimensional space, or 1,000-dimensional space explicitly? So your computation and memory use might become enormous. So that's usually a deal breaker for, say, if you have like large data sets. So this is where we introduce the famous kernel trick. So the kernel trick ensures that the operations are computationally efficient, and we also get a good classifier while doing this. So kernel trick is a very elegant and a neat solution to the problem that I've described. So instead of you creating manually creating high dimensional coordinate and computing dot products, we define a kernel function k which takes the input vectors xi and xj and simply maps it to the transformed xi and xj dot products. So this means we never have to compute this or this directly. Instead, we have a mathematical shortcut that instantly gives us the dot product in the RKHS that I've talked about. So there are a lot of solutions to the validity of k's, right? And you might ask, okay, how do I know, let's say, a particular function k that is valid for this dot product interpretation? And yeah, the answers lies in theory. In academia, we have something called the Mercer's theorem. Okay, so which says that a function k, x and y is a valid kernel if it always a positive semi-definite gram matrix for any finite set of points. So probably in simpler words, right? So as long as the matrix formed by kxi and xj is symmetric and positive semi-definite, it corresponds to some possibly very high dimensional feature space phi. And here is the list of common kernels that you might see in the wild. So one is very simple one, and you will see me using this as we move forward. It's called the polynomial kernel. So 1 plus I times xj, and this is something that is most used. This is the RBF or Gaussian kernel. So is the difference, the normed difference of xi and xj upon 2 sigma squared. Yeah. And finally, sigmoid kernels like tan h. Although a thing about this kernel is that it's not defined for all values of k and theta. So so the Mercer's theorem, as I talked about, does not hold for some of the values of k's and thetas for this. So this is not really, say, scalable as RBF is. So usually, most of the times, you'll be using in the real world the RBF kernel, right? Cool. So now, what does it entail for our dual formulation that I had computed in the previous lecture? I mean, we still need to find an objective function, but now with a kernel involved. It's very trivial. It's not, I mean, no, not trivial in the sense, but it's very simple. All we do is, so, but okay, let me just write it down, the dual formulation. Okay, so this is how it look, if you remember. Sorry. So if you recall that this is the dot product. So data is always in the form of dot product, and we also had the constraints, if you remember. So when we adopt kernelization, right, every xi xj that you see here is simply replaced by the kernel function k xi xj, right? And all the constraints remain the same. So essentially speaking, this is post kernelization, and just so instead of this, now what we'll have is and this is a fantastic thing because we can do linear separation in a hidden high dimensional space while staying in the space for original computation. So you see how this avoids the problem of making it computationally expensive, right? And this is essentially all there is to it. Okay, but for more rigor, I will do a small practical example to maybe hit the point further home. We'll create some matrices which I urge you to put it into a QP solver, मतलब quadratic programming solver like CVX OPT. So you can do that. I'll show you how to construct the matrices. Okay, so we'll consider a very small example. And I urge you to focus a little bit more now. Okay, cool. Say we have points, so you have A, B, C and D. 1, 2, 2, 0, 1, 1, minus 1, minus 1. So these points belong to class 1 and C and D belong to class -1, and we suspect that this set is not might not be nicely linearly separable, so we apply a polynomial kernel of degree 2, right? So this is the kernel. Right, so just to illustrate how this works, let's say if we had xi dot xj is equal to 3, so this is how it would look. Okay, so there is no confusion going forward. Okay, very trivial, but still don't want to take any chances. This kernel captures the second degree interactions between the features, and you might wonder why the one plus dot products comes into play. But this is just a standard form of a polynomial kernel which ensures that we also model constants, offsets and linear terms. Okay, so now we have to do is construct the kernel matrix. So to solve the SVM dual problem, we need the kernel matrix, also called the Gram matrix, as I said. So inner product का matrix जो होता है, that's also called the Gram matrix, where each entry is k xi xj. So let's compute it step by step. So this is how it would look. Xi xj compute, add +1, right? This is, yeah, sorry, add +1. Okay, so if you construct the matrix, this is how it would look, right? So Okay, x1 x1 1. Excuse me. So this is what I want you to compute and see if your answer comes to the following. So मतलब A का पेयर, A B का पेयर, AC का पेयर, AD pair, BB, BC, and so on and so forth, right? And this is the final matrix that you should get. Awesome. Yeah. So that's the kernel matrix, and remember the objective is that if you remember, this is our objective that we are trying to you know maximize. Okay, and here we typically subject to. Okay, and for our example, this would run to 4 and I would be 0. Okay, so we typically choose C to limit how large alpha I can get. So essentially controlling the margin softness, and say let's say C equal to 10. Let's assume C is equal to 10. Okay, just write it down. Right. So to solve this problem using standard QP software like CVX OPT in Python, we can transform the above into a canonical quadratic programming for. So we need a matrix P. So which is constructed as so this captures the pairwise interactions in the objective's second term. Okay, there is a vector Q. So we set Q as a vector of minus -1 entries because our objective includes the summation of I is equal to 1 to 4 of alpha I as a negative sign in the QP standard form. Okay, and we also construct matrix G and vector H. Great. So as I was saying, so matrix G and vector H. So we ensure that the constraints 0 are fulfilled. So we do this by stacking negative identity and identity, right? So specifically speaking, right, and matrix A and vector B. Finally, I'll also show you how to construct them, but I'm just listing them out for you to probably have an idea, I guess. So they represent the equality constraint summation sigma I is equal to 1 to 4, alpha I yi is equal to 0. So A is just y1, y2, y3, y4, and B is 0, right? So the solver then finds, like the solver that I'm talking about, the alpha I that maximizes our objective while obeying these constraints, essentially. So okay, the more detailed construction, I suppose. So how to do matrix P? Okay. So each element in Pij and our labels are so you can use this and the values you found in this matrix, right? And then just construct the P matrix, right? And vector Q would look like, oh my god, these vendors guys, bro. अभी निकलना है सालों को. Right. So this is essentially the Q vector. This is because in standard quadratic programming notation we actually minimize the following. That's why transpose, right? So our SVM dual is a maximizing problem, but flipping signs is how standard solvers handle it. Okay, so there is nothing. Hope you don't get confused about this. Right, so matrix G and vector H. Right, so for alpha I that's greater than 0, we get negative alpha I less than, right? Just multiply both sides by the negative sign. This leads to 4 rows in the form of and for the other constraint we get alpha I less than 10, right? So each row becomes and then you stack them on top of each other, and with for these upper bounds. So this was the lower bound, and the lower bound, and then you stack it on top of this matrix, and here H will be 0. So you ensure the size of both the matrices are the same, right? And the matrix A is nothing but and B is 0, right? So this enforces that the sum of alpha I and yi is always equal to 0. Putting it all together, and this is something that your QP solver can digest. Once it's solved, you'll retrieve the value of alpha I and find which are greater than 0, and those points are the support vectors. Compute the bias, and that's probably it. We are done. Okay, so a quick recap would be so nonlinear SVMs hand address scenarios where data cannot be separated by a single straight line. So mapping it to a higher dimensional space that can make data linearly separable, but direct mapping is often expensive, right? You cannot just iterate over multiple dimensions and see which fits. So what here the kernel trick comes into picture, which replaces explicit mappings with a kernel function kxij that does a dot product in a hidden rkhs dimension. So, and about which kernel functions are valid, we have Mercer's theorem, which says that function k xy is a valid kernel if it always yields a positive semi-definite gram matrix, and the dual formulation of the problem remains the same, except that we swap xij by the kernelized value kxij, and constructing the matrices as is you construct the kxi matrix, the kernel matrix, and then you construct the matrix P, vector Q, matrix G, H, A, and vector B, right? And if you feed all of that into a QP solver, you will get an answer. You will get a value of AIs where this is maximized, and compute the bias, and that's the that would be your final classifier. That wraps up our week on SVMs. I really hope you enjoyed these lectures. So I hope there is a clear appreciation of how a maximal margin problem can handle the trickiest data distributions by cleverly computing dot products via kernels, right? And yeah, that's it from my side. I hope you're having a good day. Thank you for watching. Bye bye.